Let's take a look at the Lewis dot structure for ozone. Ozone. It's an allotrope of oxygen that has 3 oxygen atoms. Let's figure out how many bonds are in ozone based on the S equals N minus A rule. N is the number needed to satisfy the octet. In this structure we have 3 oxygen atoms. Each oxygen needs 8 valence electrons to satisfy its octet, and so we have needed 24 electrons are needed. Available, we have 3 oxygen atoms. Each oxygen has 6 valence electrons, so 3 times 6 is 18. 18 available electrons to work with in this structure. So according to the S equals N minus A rule, we would predict that we would have 24 minus 18 equals 6 shared electrons or 3 bonds in this particular structure. Okay, according to the rules, once you figure out how many bonds you're predicting and how many electrons you have to work with, you go ahead and put the structure together. According to the rules, the first thing you do is you put the structure together. So the oxygens typically don't string together, but if there's nothing else, they must string together because there are no other atoms. So it's oxygen bound to oxygen bound to oxygen. Then you take, so we've used 4 of our available 18 electrons here. And so then you go ahead and you place electrons around the terminal atoms. So we'll let the one in the middle be the central atom and the 2 on the ends be the terminal. So we've used 2, 4, 6, 8, 10, 12, 14, 16. Got 2 more. Put them on the central atom if you have more left over. Check to see if the octet's satisfied. It is for the terminal but not for the central atom. So the rule says move a pair of electrons over to form a multiple bond. So we end up with a structure like this. Now, who's to say that we should move those pair of electrons? What about moving this pair of electrons and not moving that pair of electrons? If we were to do that, the structure that we would get would look like this. And indeed, we have 2 structures that are very similar, only in one case the double bond is between the first and second oxygens, and on the other case it's between the second and third oxygens. And sometimes this happens where a multiple bond can be found in 1 or 2 places and the structure is otherwise identical. In this case, when this happens, we say that actually both structures are correct, put brackets around them, and we say that this particular compound undergoes resonance. Resonance. What that means is that this pair of electrons and this bond right here, this extra double bond here, is the same pair of electrons that's found here, and that is actually somewhere in between the 2 extremes. So the actual molecule sometimes is drawn like this, where you have your electrons 2, 4, 6, 8 like this, and kind of a dash line here to indicate that really these are the 2 extremes, a double bond single bond or a single bond double bond, but really the actual structure lies somewhere in between these 2 extremes, and this has been experimentally proven that the bond strength of the bond between the oxygen, the left-hand oxygen and the central oxygen, and the bond between the oxygen and the right-hand oxygen is actually the bond strength of about 1.5 bonds. It's not a full double and a full single, but both of these bonds are equal, and this pair of electrons is basically resonating between the 2 extremes.